इसके सॉफ्टवेयर
We'll do the hands-on part now, and hopefully everyone has R, since I'm going to be using that. And I fixed my machine so I have the latest version of that, so hopefully everything will work. Okay, so first what we'll do is, we will, basically whatever we covered today, I just want to sort of illustrate some of the ideas. So we'll actually run some of these things. To look at the, sort of, build this sort of connection again between the matrix and the combinatorial space. So, this is one of the key, I think, something that is not really taught, very extensively. Anywhere actually, for most undergraduate degrees will focus on one aspect or the other. So in some sense you have to bring, you have to learn this in a special topics course. So I encourage everyone to go and read up on matrices, linear algebra, and how they relate to graph theory. So it's actually there's a very nice area called algebraic graph theory, and so that's where we tie the discrete graph structure with the algebraic idea. Anyway, so this is all part of that same. So we'll try to basically build this graph first. So let me. All right. So this one has, we have the adjacency matrix here, so I can copy it. Right. So this is so let's just do this in. We can do the graph first, so we can just start with the adjacency matrix. So actually, let's do the graph first. Okay, so I'm gonna. Okay. So the graph is 1 to 2 and 1 to 4, right? So I'm gonna say G is equal to graph.
We can make a ring of 1, 2, 3, 4.
Sorry. Okay, so you have to give the edges. So let me just try this first.
So please increase the font size.
Oh, the increase. Okay, sorry. I didn't get that. Okay, so actually we can give all the edges in one line. Okay, so I'm just going to say, so there's 1 to 2, right? And there's 1 to 4. So I think if I just do this, it will do the right thing. Let me see. Yeah, so it works. Okay, good. So all we have to do is simply list out, pairs of edges, right? So basically the C is a vector. So there's 1, 2, 1, 4. Then there is 2, 4. Sorry, 2, 3. 2, 4, right? And then there is 3, 4. Actually, there's more because this graph is 1 also goes to 6. So let's put it back here. 1, 4, 1, 2, 1, 4, 1, 6. Okay. 2, 3, 2, 4. 2, 1 we don't have to add, it's already there. So 2, 3, 2, 4. We already have that. Then 3, 4, 3, 7. So we already got 3, 4. So let's add let's add 3, 7, right? Okay, then you have what? 4, 5 only. 4, 5. And then 5, 6, 5, 7. And then 6, 7. So that should take care of all the vertices in our, all the edges. Ah, okay. I think that should do. Alright, so we have now our graph. Okay, so now we can say we have to plot G. What is that? Oh, yeah, sorry. Okay. So I added directly into the false. Hopefully that will fix it. Yeah. So that's our. So basically just add that option. So you have now your graph, which looks quite a lot like what we have. Okay. So now that we have this graph, we are going to create the adjacency matrix, and now I know how to do it. G is equal to as adjacency. So first I want to show one thing. So if you do as ADJ G, what this does is it returns the sparse matrix. So this will be the adjacency matrix for the graph. So I don't really want the sparse components, so I will just make it a sparse equal to false. So the sparse representation only gives the non-zero numbers, but we want the zeros also. And so I'm just going to keep that as A. So A is basically represent the graph as the adjacency matrix and make the sparse false. And this A is now the adjacency matrix.
Sir, can you please, excuse me, sir, can you, sir, a little bit slow, sir? We are doing on the tab because we are not able to.
Sorry, yeah, that's okay, that's perfect.
Can you please scroll down the screen above, sir?
So basically, first we create the graph. Is everyone there? So you have the set of edges. So this is the line. It's 1, 2, 1, 4, 1, 6, 2, 3, 2, 4, 3, 4, 3, 7, 4, 5, 5, 6, 5, 7, 6, 7. And then directly equal to 4. Everyone there? Okay, so after that, actually you can ignore all this. What we really want is this line right here. Right? So A is equal to as adjacency, as underscore adjacent, ADJ. That gives us the sparse. Okay, so now we have the adjacency matrix. So the degree, I think there's already a function called degree. So degree of G will give me the degree, vector. So I can just make this into. So remember now, I want to do first of all I want to do the inverse of the degree matrix. So I can say, so I'm going to use ID for that. Okay? So ID is the inverse of the degree matrix. It's going to be diagonal matrix, 1 over the degree. So that will do the job. So what I'm doing is dividing by the so this degree vector, right? So so it will become 1 over 3, 1 over 3, 1 over 3, 1 over 4, like that. And then you just make it into a diagonal matrix. So the diag function will do that. So if you do this, we can just quickly verify that gives me the diagonal matrix. So it's a little bit, I should probably print out only the 2 digits or something like that. Okay, so we have that. Okay, we also need the degree matrix actually. So D is simply the degree matrix, degree of the graph, and diagonal of the degree. So that will be the degree matrix. Okay. So we have that. So the first matrix we'll make is the Laplacian. So let's make the Laplacian. So the Laplacian matrix is simply D minus A. So that's easy. So we just do D minus A, and we get the Laplacian. Okay, this is what the Laplacian looks like. Now let's verify a few things. Right, so as I said, which is obviously easy to see from here, but all the row sums, in fact the column sums will also add up to 0. So if we see row sums of L, they'll all be 0. And in fact the column sums will also be 0. Okay. So this matrix L, we can try to compute the eigenvalues and eigenvectors using the power iteration approach, but since there is a function already, I can just use that function. So there is an eigenfunction. So I'm going to use that eigenfunction to compute the eigenvectors and eigenvalues of this matrix. So I can just say, let's see how it returns it. Eigen. So if you do the eigen, okay, so it said that it takes a symmetric matrix and its value. Okay, so it returns these things. Okay, return to us the eigenvalues and the eigenvectors. Okay, and they'll be returned in decreasing order. So it's doing a lot of the job for us. Okay, so that's what we want. Okay, cool. So we come here, and now we're going to do the eigen thing. So I'm going to say, I'm just going to call E is equal to eigen of A. Eigen of F. We want to find the eigenvectors of the Laplacian. So if we just do E equal to eigen L, it will compute the entire spectrum. All the eigenvalues and all the eigenvectors. So now I can print them out. So I can say E, and you print out the, use the dollar symbol to print out a field. Okay, so the field is values. So if you print them out, you will get this set of numbers. And they are sorted in decreasing order. So the largest one is up front, the smallest one is in the bottom. This, by the way, is pretty much 0. This is just a numerical, it's basically 0.8 into the 10 to the power minus 14. So it's like 0.799. And the largest one is 5.61 and so on. Okay, so this is fine. Now let's look at the eigen vectors. So I am actually interested in the 7th eigenvector. Okay. So let's take a look at the 7th eigenvector. So the way you do that is you say E dollar vectors, and the vectors are these column vectors. Okay, so you have to say comma 7. So it will pick up the 7th. So it's this. This is a matrix. Okay, this is it's a matrix which is going to be in this case 7 by 7. So the first column is the first eigenvector. The second column is the second eigenvector. Third is the third one, and so on. So all the eigenvectors are arranged in a column manner. So we're interested in the 7th column. And so we say essentially E dollar vectors. So basically this says that any row, comma 7 in the 7th column. Okay, that's basically, I'm going to call that U7. So U7 is the 7th eigenvector, and U6. So let's say I want to find two clusters. I'm going to use the two smallest, right, eigenvectors corresponding to the two smallest values. So it's going to be dollar vectors, comma 6. So I can look at what U7 is. So I look at what U7 is, and I get. See, this is what I wanted to say. So this is all the same values, okay? And the reason is that there is only, it's a fully connected graph. Okay, so it turns out that the first eigenvector that corresponds to the 0 eigenvalue doesn't really convey any information, really. I mean, in terms of clustering. It conveys information only if the graph is disconnected. So if there were two connected, if there were two components, then what will happen is that there'll be another 0, and the two parts would be, they'll have different, there'll be a different set of numbers. So this vector would be actually broken up into two components. There'll be two separate set of values, and so so the number of connected components will be the number of 0 eigenvalues. But as such, U7 we can actually completely throw out. Really, we don't really need it. This U6 is the real vector. Okay, it has a name also called the Fiedler vector, Fiedler. Okay, so this Fiedler vector, I guess, is named after the person who sort of studied these extensively. So Fiedler actually studied these, and he studied all these properties. So this notion of partitioning using eigenvectors is much older actually. This goes back to the 60s and the 70s. I think the earliest work on graph partitioning using spectral methods was in the 70s, early 70s, from IBM research labs. And they were making use of these Fiedler vectors, which is the second, So U6, so let's take a look at U6. So U6 is important, and this U6 is the one that's going to tell us something about the clustering. And I think it's obvious to you what the clustering should be. There are 4 numbers which are positive, 1, 2, 3, and 4, and the last 3 numbers are negative, and they correspond to 5, 6, and 7. So even just a one-dimensional, placement of the point in this case is enough, right? So that this one vector tells you actually what the cluster should be. All the positive numbers belong to one, all the negative nodes belong to the other. So that's kind of interesting that this actually comes out of this approach. So I would say that's very valuable information in this. So in fact, U6, the Fiedler vector, allows you to partition the network into 2 parts. Okay. Now, the earlier approaches to clustering, they were actually this recursive bipartitioning approaches. So what I showed you today was the k-way partitioning. Right? So we take the entire graph and partition into k parts. But the earlier approaches were you do recursive bipartitions. So in other words, you take a large graph, okay, use the Fiedler vector to divide the graph into 2 parts, the positive and the negative. Now you get 2 different graphs. Okay? Each one of them treat as if it's a complete graph by itself, and partition that into 2. So you'll compute just the eigenvalues, eigenvectors of one part, the other part independently, and then you recursively do that. That way also you can obtain a hierarchical, splitting of the clusters into k parts. So that's where the Fiedler, approach is extremely interesting. But what we did today is much more general. We don't have to do the recursive bipartitioning. We can do a direct k-way, k-way cut, which is more powerful than just purely recursive, partitionings. So then you might ask, okay, what if I had to find 3 clusters, right? So actually that information is here too. So actually, if you want to go to 3, I have to also look at U5. So I have to actually extract U5 from this one. And so now the point is that U7 is useless, right? So we don't really need to use it. It's really U5 and U6 that have the real information. If I look at U5, now you have actually something interesting going on. You have 0.6, 0, minus 0.6, 0, 0, 0.37, minus 0.37. So it's still not clear exactly, what the cluster should be. So, but let's, what I want to do now is I want to actually map the data into this 2-dimensional space. So the space of U5 and U6. So if I do that, then what do I get? Okay, so here's what I'm going to do. I'm going to do a matrix U, and the matrix U, let me see if I remember, yeah, so it's called C bind, because C bind will actually put a column, will put the two columns together. So I'm going to put U6 and U5 together in one data set U. And now if I plot U, that's your data. Now the interesting thing about this U is actually I can plot U. I can actually do a scatter plot of this. So this is what you get from the scatter plot. Okay. Actually, I don't know which point is which point. I just see the point. I don't know other. Yeah. So one second. Okay, so those are the points. Okay, but we need to have labels. I mean, I can look at them and figure it out. We can do it this way. Let's put the data here and then plot here. So let's see, which one is this? The first one, point 2, this is number 1 actually. So that's 1. This is number 2. 1, 2. 3 is which one? Is going to be this one. No, this one is 3. So 1, 2, 3. And I guess this is 4. So actually, it's kind of interesting. It actually, the 1, 2, 3, 4 is preserving the topology of the graph, right? If you look at the original graph, it's pretty much preserving that topology. So if I say plot G, right? So you see this 1, 2, 3, 4, 4 was in the middle. You get the same structure. Of course, 5, 6, and 7 are put in one line in this new. So I go back to this one. So these are 5, 6, 7. But anyway, the point here is I have to cluster them into 3 groups, not 2. 2 would be easy. 2 we already said. So, well, I mean, this is too small an example to really see the effect of this, I suppose. But if I were to partition this, what would probably end up happening is that the 5, 6, and 7 would be 1. And then it would just be either 1, 2, 3, and one guy would be isolated, or the other way around. Okay. So because you have to partition somehow. And here, if you look at these 4 points, partitioning them into 2 is not that clear. What we should be doing. So anyway, it's a very small data set, so we can't really see it. But at least we know what the approach we need to follow. That essentially is this data set U, which we can use to cluster things. Okay, so that's for the Laplacian. Now let me illustrate the symmetric and the asymmetric Laplacian. So let's just look at the properties of those. And I just want to see the eigenvalues should match and the eigenvectors should also be related. So let's just do that quickly. So if I want to say LA, which is the asymmetric Laplacian, which is easy because I have the inverse of the degree matrix, and I just take the matrix multiplication with L, right? So it's just pretty much inverse of the degree matrix times L. By the way, for those who are not familiar with R, if you just do this, what this does is it does the element-wise multiplication. So it does not do a matrix multiplication if you do this. So that's why we want to make sure it's a matrix multiplication. We have to do it this way. So that's your Laplacian, okay. And every row will be divided by the degree. So anyway, this is what it looks like. And anyway, I think the more important part is the eigen. So I'm going to cover the eigenvalues of the eigenvectors and eigenvalues. Is eigen LA. And now I can print out the values. And you get some, eigenvalues. The lowest one will always be 0, as we expect. And then you have some others. And they all, the other thing to verify is everything is non-negative. Okay, there are no negative numbers. On the other hand, if you did the eigen, so this is interesting to see. If you do the eigen of the adjacency matrix need not be positive, semi-definite, or anything like that. So it can have negative eigenvalues. So if I compute the eigenvalues of this, so let's just call it I don't know, just some variable. This will be z. So z dollar values, and you can see that the eigenvalues can be negative for the adjacency matrix. So adjacency matrix doesn't have very nice properties. Let's put it that way. So that's why the Laplacian, and Laplacian actually has a different interpretation also. It has the interpretation of a diffusion, a heat diffusion actually. So it comes from physics. So in physics they actually use the Laplacian in a dynamical system. It's actually the equation that comes out of heat dissipation. So that's kind of like the physical, analog. For us, there's no physical analog. It's a sort of an information flow. It's like how the information diffuses. So it's basically, again, very closely tied to a random, network. a random walk. How information, how things propagate in the graph. So one last one we want to do is LS, the symmetric Laplacian. So the symmetric Laplacian has to be the square root of the inverse, right, times L times the square root again of the inverse. So it's delta minus half times L times delta minus half. So the minus half, the half is coming from the square root, the minus is the inverse of the degree. So that should give us our symmetric Laplacian. So what did I do wrong? Oh, not delta, not dollar, percent. Okay, so LS is your symmetric Laplacian. Now how do you test whether a matrix is symmetric? That's how you test. If your transpose is the same, then you're symmetric, right? So I just tested that quickly to see whether that's true. So anyway, that's your symmetric Laplacian matrix. Now the main thing I want to do here is just to look at the eigenvalues. So you just compute the eigen LS and ES dollar values, and you do EA dollar values, and you see, there is no proof, there's not a proof, but it's just a confirmation that the eigenvalues are identical. Okay, so the symmetric, whether you're symmetric Laplacian or asymmetric Laplacian, they pretty much behave like a positive semi-definite matrix. They have non-negative eigenvalues. Now the eigenvectors are going to be different. So if you look at the eigenvectors, if you look at the symmetric dollar vectors, and let's just look at the last one, not the values but the vectors, and look at the asymmetric vector. They're just slightly different, and the difference comes from the asymmetric is all ones. They're all the same number, whereas the symmetric one, it's sort of actually proportional to the degree. So the higher degree, fourth vertex has the degree 4, so that tends to have a higher absolute value. But everything else is the same. So everyone else has the same degree. There's 3, 3, 3, 4, 3, 3, 3 in this network. So that's the eigenvector for the symmetric part. So the symmetric, but there is a relationship between them. One can kind of work out the actual relationship. they are related by 1 over the root of the degree, pretty much. So one eigenvector is equal to the other times 1 over the root of the degree plus some term, but there is a relationship. So that's that. So we basically, we can we can do that. Now, yeah, one other thing. So if you're using the ratio cut, right? So remember I said for the ratio cut, going back here, you can actually compute the precise value of the objective function. Okay, so this I didn't really go over all the steps, but for the ratio cut, we can actually compute the value of the cut. Like what would be the objective function, and that is actually given by the sum of the eigenvalues. So one can show that the objective function, I'm not sure if it's here. This just shows you the algorithm. But supposing you wanted to know the value of this objective. So where is the objective? Right here. So for the ratio cut, right, this is the objective, right? So this is the objective function, and we basically want to. So this is the objective function. So you want to know what is the value, right? If I were to do it in 2 parts, what would be the actual value of that? But actually that comes from the eigenvalue. So if you just look at the eigenvalues, so the E for the what did I use? E, I guess. Yeah. So the E dollar values. So the smallest value you can get is actually the 0, which is the last value, plus the 1.58, which is the second smallest. So this is the second smallest value. So in fact, the sum of the eigenvalues is the objective function value. That's the value of the cut. So this is kind of a nice sort of the objective function basically tells us that this 1.58, this value here is, and of course the other one is a 0. The smallest one is 0. So that's actually the ratio cut. If you cut the graph, that's the total weight of the edges that are being cut. Okay, so that's kind of a nice information you can extract from the eigenvalues. The eigenvectors help you cluster, but the eigenvalues tell you the actual objective value. That what is the weight of that cut. In this case, it's only a binary cut, so it will be just how many edges am I cutting and what were the similarities of it. So the total sum of the similarities is 1.58 or 1.59. Okay, so now let me do MCL. So I want to illustrate the working of the Mtl algorithm. So let's go to MCL. And then I'll do a few more, and depending on the time, we can do a few more things. So for the MCL, we first have to create a Markov matrix. And let me go back to my adjacency matrix. My adjacency matrix is not the one I want. I want to have self-loop. So for Markov chain, you need to have self-loop. So we're going to add a self-loop to this. So the way I'm going to do this is I'm going to make a new AA. And I'm going to call this A plus I. I don't know if they have I in, actually I may not work. Okay, let's define I first. So I is the identity matrix, and so it's going to be basically a diagonal of, actually there should be an easy way, let me check if there is one. In MATLAB they have I guess not in this one. Alright, so I is equal to diagonal C rep 1, replicate 1 7 times. Maybe that will work. Let's see. 1, 2, 3. So all I did is I took, let's verify it worked. So what I did is I took the number 1, I replicated it 7 times, and I could have written 1 7 times, but I just made it. And that C is just, C makes it into a vector, right? So C is just, whatever is inside will turn it into a vector. So C of replicate 1 7 times is just a vector of 7 ones. And then I make a diagonal matrix of those ones. And so now I can make my Markov, adjacency matrix, which is the original adjacency matrix plus I, because I want to add all self loops. So it's just A plus I. And we can verify that. So now there are 1 on the diagonal, everything else is the same as before. Okay, so now that I have this, I have to of course redo the degree matrix. So I want to do inverse of the degree matrix, and I'm going to redefine this with respect to the new matrix. So it's going to be 1 over, sorry, the inverse is, yeah, 1 over, no, diagonal of 1 over degree, actually not degree, so this would be just row sums AA. This time I'm using the row sum because my graph has changed, so I can't just use the degree of the graph. I've put those self loops. So that's my inverse of the degree matrix. Okay. So that works out fine. And now I can create my Markov matrix. So the Markov matrix is simply the inverse of the degree matrix times the adjacency matrix. So we just do the inverse, delta inverse times the adjacency using my Markov matrix. So let's look at M. So this is properly normalized, right? Everything basically, all rows add up to 1. You can verify that. Okay, so it is row stochastic. Just to verify, the columns should not be generally, add up to 1. So it's not column stochastic. So we say it's a stochastic vector, means it's a transition vector, probability vector. So the rows are stochastic, but the columns are not stochastic because they're not probability vectors. So one question that we discussed is what is the two-step Markov? What is the two-step transition matrix? So M2 should simply be M times M. So here's your two-step, matrix. So this one, let's verify it is stochastic. And I mean, again, it's not a proof, but it's easy to prove this, that all your will be, they will always be row stochastic all the time. Now, I'm going to do this in a loop. So I want to see what happens, right, as I increase t. So this is without any inflation. This is simply walking, right? What is the probability of landing up in a node after t steps? So let's just make up something. So this time I know how to do it. I in 1 through, let's make it 20 steps, right? Hopefully that should be enough for it to converge. And all I'm going to do in each step is I'm going to basically create a M, let's just call it M new, for example. It's going to be, actually let's do one second. So let's just make a temporary matrix Z is equal to M. And I just update Z so I don't destroy my M. So for I in 1 through 20, let's say, what I want to do is I want to say Z is equal to Z times Z, right? So just keep on expanding the walk by 1 more step each time and put the result back in Z, because I want to reuse that same variable and then close the loop, and that should do it. So now we have had basically a 20 step Markov process. So what happens after 20 steps? So let's look at Z. And let's look at the first row of Z. So that's your probability of ending up. So if you start from vertex 1, you can end up with other, in other states with that probability. If you start at vertex 2, you end up in other vertices with that probability. And actually all of them should be the same, because they'll all converge to the dominant eigenvector. Okay, because that's what the dominant eigenvector theory says, that no matter where you start, ultimately the eigenvector, right, is a fixed point. So the probability of being in a given state is the same irrespective of where you basically and how you begin. So that's the problem with this approach, is that if you simply just do this, everything converges to the dominant eigenvector. So let's look at the whole Z. So that's your whole Z. Okay? So you have essentially all the rows are the same, and you can verify this very quickly. You can actually compute the eigen of M. Or maybe the M transpose, I have to check. Okay, so if I do eigen M, what do I get? Eigen M gives me that. Here. Okay, I have to turn it into a probability vector. Okay, so this eigenvector, it's not yet a probability vector, right? So I have to make it into a probability. So look at the dominant eigenvector, right? So what I'm going to do is I want to make it into a. So take U. Sorry. Each dollar vectors number 1. So that's what makes it U1. And just say U1 divided by sum of U1. And this should be exactly the same as our, right? Look at Z1 is identical, right? So the dominant eigenvector of the transpose, because that's when you do the column operation, it actually turns out to be a transpose thing. So I've just verified that every row of your your 20-step transition matrix actually converges to the dominant eigenvector. So let me just respace what I did. So basically what I did is I took my Markov matrix and I computed the eigenvalues of the transpose, right? So the eigenvalues and eigenvector. So you look at the first column here. So the first column tells you this is your dominant eigenvector, the first eigenvector. Now you look at this and you say, oh, it's not the same as my transition probability. But that's because this is just a normalized vector in terms of the unit length. We have to make it into a transition probability. So you just take the vector and divide each entry by the sum of all the entries, okay, which is exactly what I did. So I took this vector, the first vector is U1. So I took the, U1 is the first vector, the dominant eigenvector, and then I just divide by the sum of all the entries. So I make it into a stochastic vector. And that turns out to be, this vector right here. And this is exactly the same as what my walk converged to. So these are the probabilities of lining up in a given node. So anyway, this is basic, as I said, transition in a Markov chain theory basically tells us this. So this is not what we want, because this is every row will converge to the same thing. So now we have to do the MCL idea, which is you have to inflate. So I'm going to change my approach now. I'm going to again start with Z equal to M. So start with your one-step Markov matrix. Let's make R a parameter. Let's make it 2. Okay. Or let's keep it 2.5 because I know it works, right? In my example, it will give me 2 clusters. So if I make R equal to 2.5, and I just now basically code up the method that I had before. So what we want to do is we want to do inflation. So let's first define a function called inflation. Okay, so you can just say inflation is equal to actually function. I'm not sure, I have to check. Okay, so what is our inflation? Oh, sorry, it has to take two things. Let's close it up. So I have to actually, it has to take two parameters. So inflation is a function. Okay, so this is how you define it. Of z and r, right? Okay, so what I want to do is I want to take some matrix, and I want to basically take the rth power of that matrix. So that's actually easy. So I'm just going to set up a temporary matrix called, let's call that f or something. So f is simply z to the power r. So this is actually just one step. So all the entries will be taken to the power r. Okay, so that's easy. And then what you have to do is you have to make sure that after you do the inflation, you take the rth power, you have to normalize everything. So what I'm going to do is I have to divide every row by its sum of the rows. So what I can do is I can say rs equal to row sums of f, right? So now I have all the row sums, and then I have to check whether this will work. I can just say f is equal to f. Question is which entry will divide which one, I'm not sure. I want to say this, but I'm not sure if it will work. But I do know the following will definitely work, so let me just do it this way. IRS, if you remember my diagonal of RS, right? We'll use the same trick, dividing the rows by a number. So I'm going to use the same trick that we did for the degree. So if I take the row sum as the degree, which is what it is actually. So it will be diagonal of 1 over RS, and then I can say that f is equal to IRS multiplied by f. So that will definitely, hopefully, I mean if I've not made any other mistake, that should work. And that's it. So let's see if this works. Let me make up a small matrix and see. So I'm going to make a matrix A is equal to matrix. This is something I'm just doing for my own verification. So just make it 1, 2, 3, 4, 2 by 2. So there's a matrix of the inflation of A and power 2. Oh, it didn't return anything. So I have to actually try to print something. Okay, there you go. Does it work? No. What do you do? Oh yeah. So if you do 1 squared plus 3 squared would be 10, right? So you see it did the right thing. So I guess the code worked. So that's good. So my inflation is working. So this is just a subroutine that I'm going to call, right? So if you want to go back and just take a quick look. So basically the inflation function is taking your sum matrix, a square matrix, and the inflation parameter. It first takes the powers of that matrix, and then that's the easy part. And then you have to make sure that you make it into a probability vector, so you have to divide by the degree, divide by the row sum. So to divide by the degree, I use the same trick of inverting it, and then I multiply the inverted degrees times the F matrix to get the normalized F matrix. So basically it remains the Markov matrix after the inflation. And so we just quickly verified that this whole process actually works. Alright, so now we can begin the actual MCL code. So we start with M. So I'm going to make Z equal to M. And now we just do a for loop. And I'm not going to write the logic of when it converges. So I'm just going to let it run for, I don't know, 20 iterations and see, hopefully it will converge within that. So I'll just say I goes from 1 through 20. And then all we do is, I in 1. IN. Okay, now what we first do is we first walk one step, right? So Z is equal to Z times Z. This is our standard one-step Markov walk. Now we do the inflation. So I basically just call Z equal to inflation pass Z to it and pass R to it, right? So R is 2.5. I had set that to 2.5 before. So it's defined. And that's it. I mean, there's nothing more to do. So it's as simple as actually this code. And let's see what happens after 20 iterations. So now I can look at Z and see what happens. And actually it has converged. It has converged exactly to the figure I told, which I had in my example. So first thing first, so how do we extract the clusters from this? First you look at the diagonal entries, okay? Any entry in the diagonal is an attractor. Okay, so the vertex number 4, the 4 entry, right? The diagonal entry is a 1. That means 4 is going to be an attractor. Who else? 5 is not, but 6 and 7 are both going to be attractors. Which is what, if you remember from the figure, I'll show you in a minute. So let's go back to the figure and take a look. So this is the figure I had showed you, right? So you see the 4 is the attractor, the gray node. The 6 and the 7 are the gray nodes, and they are the attractors. And now we go back here and the values on the edges. So this is where you look for who is attracted to 4. Okay? So if you see an entry, if you have an entry I4 entry, okay, so look at the 4th column. Anything in the 4th column, which is the non-zero, is going to get attracted to 4. Okay? And you can see that 5, 6, and 7 are 0. That means they are not attracted to 4, only 1, 2, and 3 are. And the value is what I put in this graph here. See? So 4 is a self loop, the diagonal entry is a 1. 1, 2, and 3 with a value of 1, they get attracted to 4. Then we do the other cluster. The other cluster, 5 and 6 are both attracted. And then look for who is attracted to 6. It actually, it's everyone. It's actually 5, 6, and 7. All the entries are really attracted to 5. And the same is true here. Actually for 7, both 5 and 6 are attracted to 7. But these attractors, that's why I drew that at the undirected edge. Actually the edge goes both ways. I mean, I could have just put 2 arrows on both ends, it would become it's pretty much like so the direction basically goes both ways. So these 2 attractors are attracted to each other. Of course, they have a self loop. So only the self loops are the attractors because the diagonal entries are, have to be non-negative. And then 5 is attracted to both. And so once you have this graph, finding the connected components is extremely easy. So you just find the connected components and so, but you see, I mean, this kind of, very few lines of code you can actually do something very interesting actually, because the power, all the libraries are out there. Now the real challenge of course is how to scale this up, right? So if I say do this on a matrix with a billion nodes, right? Do it on a Facebook network, that's where the challenge is. You have to do this in a distributed manner, you have to optimize things, you may have to approximate, right? So that's where the cutting edge of the research is in terms of, or you come up with a new algorithm, right? So you have either a new algorithm or a better, faster, computationally more efficient approach, an approximation. So that's where I would say the cutting edge of the field. Okay, so is there any pressing request for me to show you anything else? Right. So basically, I think the point here is that the combinatorial and the algebra goes hand in hand, and there's some nice results that we can obtain looking at the graph from these perspectives. So, yeah.
If we take the R less than 1, I want to analyze what happens.
r less than 1 is actually, if you look at the physical meaning, right? You are basically saying that that take the roots of the thing, and so it is a nonlinear. Actually, that's interesting. I'm not sure if the method converges. I have to check. So the convergence, I think, depends on r being greater than 1. If you are less than 1 and you're doing the inflation, you're taking, so let's take 0.5 for example, right, which is the root. So if you take a square root of the values, okay, what would happen to your parameters? So you're actually decreasing. It's kind of like the opposite of what you really want. I mean, you're basically saying that even if you have high probability, you're going to lower it. That means you're saying walk even further and further away, right?